My system is a smart shower system which is designed to prevent people from wasting water and having excessive heating costs by spending too long in the shower. It does this by limiting showers to 4 minutes because the solenoid component here has a valve which is able to turn on or off and to control the flow of water through the shower. The other component is a touchscreen controller which enables the user to authenticate with the system so that only they are able to enable their shower and start the shower. It has a lockout so that the user is not able to have more than 3 showers a day or showers closer than 1 hour together to prevent them from stacking them together and having an excessively long shower. But it will allow multiple users to authenticate to have showers one after the other if required. The way it works is probably best seen from the breadboard. It has a 15 volt battery pack provided by these 10 AA batteries, which powers this 15 volt rails here. It uses a buck converter which acts as a efficient power supply to convert this down to the 5 volts, which is used for the other components in the system. The buck converter works by drawing power alternatively from the batteries or from the charge that's been built up in the inductor coil, allowing the battery source to be turned off for significant portions of the cycle. And the voltage here will go from slightly below to slightly above 5 volts in a sawtooth pattern. That's been smoothed out by using these capacitors, and I've got multiple capacitors because that allows them to handle more current without getting hot. My solenoid is meant to draw 800 milliamps, but some solenoids perhaps draw more than that for brief periods, so I've got a 3 amp inductor here and multiple capacitors. This should be able to handle at least up to 3 amps if required. The solenoid itself is a latch solenoid which uses a permanent magnet to hold the valve in position without needing energy, and a coil which can be charged either with one polarity or the other, which will push the pin open or closed. This requires only a brief 20 millisecond pulse of current to open or close the valve, and there's no current that's required to hold the solenoid open for the remainder of the 4 minutes in the shower, which is what an ordinary solenoid would require. So this is a significant power saving. It's controlled by this motor driver, L9110, and this contains an H bridge that is controlled by these 2 input pins. When one of them is high and the other one is low, it enables current flow one way, and when that is reversed, the flow is enabled the other way. When both the pins are high or low, no current flows, which enables it to be in a low power state for the majority of the shower or the time where nobody's using the shower. The system communicates with a Bluetooth module between the solenoid controller and the Raspberry Pi touchscreen, and this uses Bluetooth 4 from the HM10 module, and this has significant power savings over Wi-Fi or Bluetooth 2, which is why I use this system. It also contains a flow sensor, which is another part which contains a turbine which turns as the water flows through it, and a Hall effect sensor converts that into square wave pulses which are sent in on this pin here, enabling the flow of water to be counted. There's 1 pulse, there's 450 pulses for every litre that's received. The remaining part of this circuit is a voltage divider, which is used to reduce the 15 volts normally from these rails down by 30 over 230 to give a voltage around 2.25 volts maximum on the analog input pin. And this is compared against the voltage reference, which is calibrated using this system. The diodes prevent temperature from interfering with the voltage, and the potentiometer here allows for the output to be calibrated so that the external reference voltage is 2.49 volts. This enables an accurate voltage measurement. I did find that at 12 volts, which is what I was initially using, the solenoid was not reliably able to open if the water was turned on. However, at above 12 volts, it seems to work reliably. So that's why I'm using 15 volts. And the user will receive email alerts if the measured voltage is less than 12 volts to alert them to change the battery. The system can close the valve with less voltage, however, so the system should still be able to close even if it doesn't have enough power to open the solenoid to begin the shower. It should still be able to close the shower and lock the flow of water, preventing leaks or unauthorized use as the batteries were depleted if they weren't changed in time. The other section here, which in my final build I built on the lower part of the breadboard, is the Amiga 328P chip. This is the same chip that's in the Arduino Uno, but I found that it uses less power when it's used standalone, probably because it doesn't have the LED and some of the other circuitry that's on the development board. I did need to use the 16 megahertz crystal, which enables more accurate timing, and it's got these two capacitors that help it to oscillate. And I need a smoothing capacitor here, which prevents the ripple current here from affecting the power supply to the chip itself. This resistor here is used to enable it to monitor the input from the Bluetooth module. This is 5 volts. So it can't be passed directly to this interrupt pin here, but this 220 ohm resistor is used to protect it from over voltage. And so when the pin becomes low during transmission, that will be detected as an interrupt here, and that will allow the system to wake up. Similarly, the other interrupt pin on this chip, there's only two pins, D2 and D3, is the signal from the flow sensor. So if the system is in sleep mode, which occurs when the solenoid is closed and it hasn't received any input for the last 10 seconds, it will go to sleep and reduce its power consumption from 25 milliamps down to 0.57 milliamps. And it will remain in a sleep state until it receives either a Bluetooth signal, which wakes it up, or there's an unexpected flow through perhaps a failing solenoid, or someone has bypassed the system somehow, and that will also wake it up. And then sensor readings will then be sent through Bluetooth back to the Raspberry Pi controller, which enables the condition to be reported to the user so they can inspect for leaks. The touchscreen controller, I printed a case. It's designed to be 3 millimeters thick in most sections and closed with Gorilla Glue, which should help to make it splash proof. It's got this piece of rubber, flooring rubber, 1.5 millimeters thick, to hold it over the top to prevent leaks, and a resistive touchscreen on top of the Raspberry Pi. Because of the tolerances of the case, I used an extra piece of rubber just to hold it out a little bit higher so that it would fit nicely with the piece on top. And inside it contains a 3.5 inch resistive touchscreen, so it needs a little bit more pressure than the capacitive touchscreen in order for it to register a press. But the advantage of this type is that it isn't affected by water, so that any water on here will not be detected as a press, whereas with a capacitive touchscreen, it will alter the capacitance and would be detected as multiple key presses, rendering the screen useless if you've got wet fingers or humidity in the bathroom. Inside this, the advantage of this particular touchscreen is that it still allows access to the GPIO pins, even though it's connected to the Raspberry Pi. If I carefully remove this, you can see that I have a piezo buzzer here, which enables me to use pulse wave modulation to emit tones to inform the user when the water's about to start or about to finish. And this is connected up to the ground pin and also to pin 18, which is the pulse wave modulation channel 0 pin. It's the only one that can be used for the hardware interrupt. And that nicely fits in here and enables me to fit it all together into the case. And that is my touchscreen controller. This is the sketch for the shower solenoid controller. It uses the sleep library to control going to sleep and waking up, which I'll show later. It's got some initial constants defined to make it easier to see which pins are being used at various points in the program, and some constants that I use to again make it easy to control various parts. The global state here is used to store information between calls to the loop or various functions. The first one here is the flow count, which is volatile because it's altered during an interrupt, and that's used down here. Every time a pulse is received on the input pin, it will increase the counter. And this is read and reset once every second so that the flow in litres per second is measured. There's a boolean that stores whether the valve is currently open or closed. And it's 3 timers which are used to determine when the sensors were last read, when the shower was last open, and when the last communication was received from the Raspberry Pi. And these are used to make sure that the sensors are read every second, the shower is turned off after 4 minutes, and the system goes to sleep after 10 seconds of inactivity, providing that it's not in the middle of someone's shower. So initially, the system needs to configure the serial output to the Bluetooth. So it uses the standard baud rate, which was found to be sufficient for the amount of data that I was transferring. It then sets the solenoid to a closed condition so that if the power were to fail, that would not be a way to keep the system turned on. It sets up the pins that it's monitoring as input to reduce their resistance and enable them to be read. And it sets all of these counters to an appropriate state so that they will all be ready to read the sensors, etc. The way that Write Solenoid works is it sends, based on this boolean, which says whether it needs to be open or closed, it will send either high to one pin and low to the other, or vice versa, which passes the current through in one polarity or the other through to the solenoid. It then waits for the 20 millisecond period to enable the solenoid to change state, and then it sets them both to low, which is, if you remember, where no current passes through the motor driver, saving power during the hold condition. This is the counter, the interrupt that simply increases the counter. And if we want to read the other sensors, to read the flow rate, we simply read the value of this counter and convert it, divide it by 450 pulses per litre to get the volume in litres. And because this is read once per litre, it will give a volume in litres per second, and the count is then reset so that it will start counting for the next second. To read the voltage, first it receives the count, which is a number between 0 and 123, which represents the voltage compared to the reference voltage. This is then divided by the factor which has been calculated based on the resistances that I used in my resistor divider. So that converts the 2.25 volts back to 15. And then because this is a count, it needs to compare that against the reference voltage and the resolution to give the value in voltage. And this is then returned. In the loop, it first checks the time in milliseconds since the system was turned on, and if it is now time, the shower is open and it's time to turn the shower off, then it will do so, and it will reset the watchdog so it will start counting down the inactivity period. However, if the solenoid was closed and we've had 10 seconds of inactivity, then it will call go to sleep, which I'll explain later. It checks to see whether any input is available from the user. In this case, the Raspberry Pi will send the lowercase o if it wants to open the valve, and this will open the valve and reset the timers so that the shower countdown will start. Finally, it also looks to see whether or not the sensors have been read within the last second. If they haven't, then it will read the flow and voltage sensors, and it converts them into a string, which is then sent through the serial port to the Bluetooth sensor and received by the Raspberry Pi. There's no need for error checking here because the signals are sent every second. If one was lost, it wouldn't be a significant issue because a new reading is going to be sent a second later. And going to sleep, this uses the sleep library. It enables sleep mode initially. It resets the interrupt, so instead of going to the normal control to count the flow, it instead goes to a wake on flow or a wake on Bluetooth interrupt. The wake on flow occurs when the low signal rises, and the wake on Bluetooth occurs when the 5-volt signal during inactivity drops during transmission. And these interrupt handlers here, which reset the interrupts back to the original position and count the pulse of the flow if it was a flow interrupt that woke the system up. To ensure that the system does wake up, we have to ensure that the system has interrupts enabled. Otherwise, even despite triggering on the pin, they wouldn't be called. This is normally set, but I call it here just to be sure that they are enabled at this point in the program. The sleep mode, there are a number of sleep modes. This is the most efficient sleep mode, which powers down to perhaps 0.57 milliamps while it's asleep. And it does, however, preserve the values of the registers so that when it wakes up, the values for the timer, whether the solenoid's open, and the flow count are still maintained. This then puts the system to sleep, and it will remain here asleep until one of these interrupts is triggered, which is handled, and then it will disable sleep mode and reset the watchdog timer so that the system doesn't go straight back to sleep again, thinking that there's been a period of inactivity. So that is the solenoid component. The touchscreen component has 3 services, one for the user interface, one for the Bluetooth, and one to control pulse wave modulation through one of the hardware pins, which enables a piezo buzzer, which is in the case, to play tunes to enable the user to know whether the shower has only 1 minute remaining, so that they're not surprised when the water suddenly turns off. Finally, it also has a cron job here, which will monitor the readings which have been sent to the log file, and if there is a condition such as low battery voltage or unexpected water flow, this triggers a webhook via IFTTT to send an email to the user. The way it works is the user interface it uses LVGL, the Lightweight Versatile Graphics Library. This is programmed in C and is designed to be efficient for embedded systems. Perhaps it is smaller than using another library like Qt, but I found that it still produces quite large executable size, so perhaps in my next project I might use a different library. When it starts, it creates the screens, it loads the user's details from a file, which enables their name, password and the times of their last shower to be stored on the SD card. And then it goes through and updates the event handlers based on events that occur, like the user pressing the touch screen. And these are used to control the showing and functions within the other screens. For example, the main screen has an event handler when the button is clicked. If the user clicks on one of the icons for themselves, then it will open the login screen for that user. The rest of the code is simply setting up all the buttons, etc., and handlers in the appropriate position. It has a screensaver, which is used to display a blank screen until the user presses the button, and when they do so, then they will go back to, oh sorry, that's not the screensaver, this is the blank screen, here we are. It has a screensaver so that when the user will initially see a blank screen, and when they press a button it will go back to the previous registered screen that the user was viewing. It has a login screen which displays a number of buttons and allows the user to enter in their password, compares the password against the password that was stored within the file, and if the user has logged in, then it goes to the shower screen. And this shower screen has just one button, and the button is updated to tell the user whether or not they are able to have a shower, whether how much time they have left, or if the shower is unavailable because they've had a shower in the last hour, or they've had 3 showers within the last day, how long they have to wait before they can have their next shower. And when the user does click on the button, it sends a command to a named pipe, which controls the Bluetooth component here. So this is a separate system which is able to be opened or closed as required. It monitors the input from the shower here, and when it receives the appropriate input, it will instruct the music service to play and to schedule and play the appropriate tunes to signal the shower is starting, and it sends a wake up command to the device to ensure it's awake, and then sends the lowercase o command to open the solenoid. The system is designed so that if it were to fail, it would receive a not connected interrupt, which would then close the service, and System D is designed to restart the service whenever it quits, so that the system will then restart, ensuring Bluetooth connectivity is re-established. When the system does establish a connection, it subscribes so that it then receives any input from that device. It comes here to be checked, and if the input is coming from the appropriate handle, then it will be added to a buffer, and when the buffer has enough information for the entire line of data, that will then be processed to extract the flow rate, the voltage, and whether the solenoid is currently open or closed. And this is then sent to the log file, which can then be monitored by the other parts of the system. The pulse wave modulation contains this system, which monitors the log file, temp music, and when a command is sent to temp music, it will schedule at appropriate times tunes to be played. The first tune is played immediately to signal the water starting. The next tune is played at the 3-minute mark to show that the system only has 1 minute remaining, and the final tone is played at the 4-minute mark to indicate that the water is being turned off. And it uses a separate thread because this processing the user input is a blocking command. So it uses a separate thread to monitor the current time and see which tunes are currently scheduled to be played. When it is time to play one of the tunes, it will call, here it is. It will call the appropriate function here, which will enable the pulse wave modulation and play the various notes or play a sliding tone, which is what we play to drop from 1 octave over a length of time when the user has finished their shower. And this works using hardware pulse wave modulation. There's only one pin that can be used for hardware pulse wave modulation on the Raspberry Pi. It's GPIO 18, which is connected to channel 0. And there's a number of things that are required. There's a pulse wave modulation overlay, and this section needs to be run as the root user. And that's why I've designed this as a separate service, because this enables this privileged portion to be run as the root user, and the remaining services can all be run as the regular user. And it communicates with this system class pulse wave modulation with the appropriate chip and channel, and it turns on the duty cycle and sets the frequency appropriate for the note that the user wants to play. Or it can turn the duty cycle off if it wants to produce a period of silence. And that is how that functions. So those are my 3 systems, which are controlled by System D with files such as this, which enables the service to always be restarted if it were to quit unexpectedly in the middle of the system, ensuring that it remains up and robust in cases of failure. Finally, I have a cron job which runs once every hour to monitor the data that's in the log file. It simply looks at the last hour's worth of readings and checks whether the readings indicate that the battery voltage was low. It detects the lowest voltage that was measured within the last hour, or it detects if the solenoid was closed and there was some water flow measured, and so it measures the total volume of water that's flowed while the solenoid was closed within the last hour. And finally, after the log's been processed, it then checks to see whether or not an error condition was met, such as the battery is less than 12 volts or a leak was detected, and then that triggers through this webhook for if then that to send the appropriate message to the user that something has occurred that they need to check. So that is the functioning of the two components of the system, and now I'll show it in action. So initially the shower is locked, and to activate it the user needs to log in as a user. Let's say Bill wants to have a shower. He needs to enter his password and then he can start. We hear the sound, we heard the solenoid click, and the water is activated. The screensaver comes on after 1 minute. If Bill wasn't in the shower and wanted to see how long he had left, he could press the button to activate it. Or if the screen's active and he wants to update, he can also press. The warning tone announces that Bill has only 1 minute remaining. And at the 4 minute mark, the sound announces that the shower's finished and the solenoid turns the water off. It's still recommended to switch off the tap at the mixer to avoid leaks. If Bill were to try to have another shower now, the system alerts him that he's not able to have a shower for the rest of the next hour. However, if Anne wanted to have a shower, she would be able to log in and start. Compared to existing systems on the market, my system is cheaper to build, easier to install, doesn't require an electrician for additional power points or a plumbing cabinet, and is optimized for battery life and provides a convenient user interface via the touchscreen. Additional modifications I would like to extend would be to add a mosquito server for integration with existing smart home systems, a web server to display graphs to help educate users and enable behavior modification. And I had attempted initially to use a temperature sensor, but I found after waterproofing it and attaching it inside the shower head that it was not able to provide a rapid response, so it was not reliable or usable for the purpose. However, if a temperature sensor could be integrated to this system, that would allow real-time monitoring of water flow and temperature, enabling electricity and heating costs to be calculated as well as water usage.